Assalamu alaikum. This is lecture 20 of data security and encryption, and in this lecture I am going to discuss about RSA algorithm. So here are the lecture content. In this lecture we will be studying about the description of the RSA algorithm, and there will be some discussion about the computational aspect of cipher using the RSA algorithm, and finally there will be some discussion about the pros and cons and security of the RSA algorithm. So this lecture is in the continuation of the previous lecture about the public key encryption, and the two famous scientists in the field of network security named as Diffie and Hellman introduced a new approach to cryptography and challenged the cryptanalysis to come up with a new algorithm that can meet the requirements of public key system. And after that there are a number of other algorithms that have been proposed for public key cryptography. Some of these though initially were very promising, but they are somewhat breakable. And some of these algorithms, there was some successes, and one of the first successful response to the challenge that was developed in 1977 by an MIT scientist named Ron Reverest, Adi Shamir, and Len Eldman. It is the most widely used general purpose approach for the public key encryption, and the name of the algorithm is based on the name of the authors. So RSA algorithm is a cipher in which the plain text and the cipher text are integers, and they range from 0 to n minus 1 for any given n. A typical size for the number n is usually 1 kilobits, and that is 124 bits or 309 decimal digits. So here is some description about the RSA algorithm. The RSA algorithm makes use of an expression with the exponentials. So plain text is encrypted in blocks, with each block having a binary value less than some specified number n. So encryption and decryption are one of the following forms. For some plain text block referred as M, as you know it was previously referred as plain text P. So now it is referred as M, and the cipher text is again a cipher block represented as C. So whenever you have to encrypt a message using the RSA algorithm, the cipher text will be equal to the power of the plain text with the number E and taking words with the number N. So E is a encryption algorithm. So to decrypt the message, again to get the actual form in the M, you have to take the power of the ciphertext with the number called D, a decryption, and take the mod with the N. So this is also elaborated again with the M raised to power E into D, which is the combination of uh, encryption and decryption on the original text to get the final text. So both sender and receiver must know the value of n, that is the public key. The sender knows the value of E, that is encryption, and only the receiver knows the value of D, which is decryption number. So this is a public key encryption algorithm with the public key PUEN. So E is the private part which is available for the sender, and N is the public part which is available for the for both the parties. And the private key which is used to decrypt the algorithm, it is only available to the receiver, as the D is the decryption part and N is the public part. So the algorithm also requires certain preconditions to be met. So for this algorithm to be satisfactory for public key encryption, the following requirements must be met. First requirement states that it is possible to find the values of encryption, decryption, and the number n such that if you take the power of the plain text with the encryption and decryption mod n, it should be equal to the uh, original text. And for all m, the m should be less than the number n. So the second requirement states that it is relatively easy to calculate this encryption and the decryption functions for all the values m which are less than n. And finally, it is feasible to determine a d, the decryption value given the encryption and the numeric key n. So this figure summarizes the RSA algorithm, so in which we have two participants A and B. A is referred as Alice and B is referred as Bob. So Alice generates a public or private key pair, and Bob encrypts using Alice's public key, and Alice decrypts using her private key. So for this example, the keys were generated as follows. So first of all, you have to select two random prime numbers p and q, and p and q should not be equal. That means you should have to select different prime numbers. So for an example, we select p is equal to 17 and q is equal to 11. So the next step is to calculate the number n by multiplying p and q. As for this example, if we multiply 17 by 11, the resulting n will be 187. So next is the to calculate the totient of the function n, which was discussed in the lecture number 5. So if you recall the calculating totient function, you can calculate the totient of n by multiplying p minus 1 into q minus 1. So in this case, the p minus 1 will be 16 and q minus 1 will be 10. So we will have the totient of function of n that will be equal to 160. So the next step states that the select an encryption E such that E is relatively prime to the totient n, that is 160, and it should be less than 160. We can choose any number of E. So in this example, we can choose E is equal to 7. So both conditions are met, that it is less than the totient function and it is relatively prime to the totient of n. The next step is to determine the d such that if you multiply d with the e, the result should be 1, and the d should be less than 160. So the correct value is for d in this example is approximately 23, because 23 cross 7 is equal to 161, which is 160 plus 1, and if you divide the result with 160, you will get the remainder 1. So you will have the d is equal to 23. So this can be calculated using the extended Euclidean algorithm. So you can find out more information in the lecture number 5. So the resulting keys for public key encryption are referred as E and N. So in this case, we choose the E as 7 and N as 187. So this is referred as public key. The private key is referred as PRD of N, which is equal to 23 and 187. this example shows the use of these keys which we discussed in the last slide for a plain text of input m is equal to 88. So for encryption we need to calculate the ciphertext C, which is equal to 88 raised to power 7 mod 187, which is equal to n. So if you recall the formula, which was m raised to power e mod n for generating the cipher. So in this case we use the key of encryption as public key, which e is equal to 7 and n is equal to 187. The result is equal to 11. So for decryption we use the formula C of D mod M. So in this case C is equal to 11, the decryption key was 23 and N is 187, and the result is equal to 88. So this figure illustrates the sequence of events for the encryption of multiple blocks and gives the specific example in the second option. The circle numbers indicate the order in which operations are performed. So if you take the order for the first general approach to generate a sequence of events for encryption in the multiple blocks, we have a random number generator which will generate a random number E, P and Q. The requirements are illustrated in the previous slides, that P and Q should be prime numbers and they should be different numbers than each other. And E is a random number which is also less than the quotient and also prime to the resulting quotient. The second step is to multiply the P and Q to generate N and generate the public key E and N for the encryption. Then you have a plain text P, which is a decimal string, which is a plain text, and you have to convert it into a decimal string, and you will get a block of number for the RSA algorithm, and you perform the function for each block of the text to generate the cipher text. Next process is transmitting to the receiver, and the receiver has its private key in the form of D and N, and it recovers the text from the C to the original P, and the receiver gets the final text. So this second diagram shows the example in which a sender is generating a text, how are you, to send it to a receiver. So again we have chosen two random numbers, P is equal to 73, Q is equal to 151, and an encryption number random that is equal to 11. So we generated the key E is equal to 11 and N is equal to 11,023. So on the other hand, we convert these numbers, these plain text into the numbers, and we get this sequence, and each sequence is converted into uh, four letter or 4-digit literal. So then you calculate the ciphertext for each literal and finally transmit it to the receiver. The receiver has the decryption key, and it uses this decryption key on the received ciphertext to generate the original keys, so which are equivalent in both the diagrams. So the RSA uses exponentiation in modular arithmetic, and both encryption and decryption in the RSA involve raising an integer to an integer power mod n. As you have seen, you have raised m to the power e and c to the power d. So it can make use of the property of the modular arithmetic, which states that if which states that a mod n x multiply by b mod n into mod n is simplified as a multiplied by b into mod n. So if the exponentiation is done over the integers and then reduced to the modulo n, the intermediate values would be very high. Therefore, this shift reduces a large number of computation, and then we can also reduce the intermediate result modulo n. This therefore the calculation will be very much less than this form. That means you do not have to calculate the modulus n for each number and then multiply those to calculate the mod for the resulting sum. So you can multiply both numbers and then take the mod, which will greatly reduce the calculations. To see this efficiency might be in very high, you can consider a simple example. For example, if we wish to create uh, wish to exponent x to the power 16, so a straightforward approach will be multiply x with x for the 16 times. However, you can also achieve the same final result with only 4 multiplication if you repeatedly take the square of each partial result. For example, the initial multiplication will be x multiplied by x and you will get x square. Second multiplication will be x square multiplied by x square, which you will get x raised to power 4, and then you can multiply these to get the result in 4 computations. So to speed up the operation of the RSA algorithm using the public key, a specific choice of the encryption E is usually made. So the most common choice for the E is 65,537, that is equal to 2 raised to power 16 plus 1. So the two other popular choices for E are E is equal to 3, which is equal to 2 raised to power 1 plus 1, and E is equal to 17, which is equal to 2 raised to power 4 plus 1. So each of these choices have only two 1 bits. For example, in the 3 you will get only 1 1, and in case of 17 you get 1 0 0 0 1. And similar case is in this example. So suppose if you use e is equal to 3, this is a very small public key and RSA becomes very vulnerable to simple attacks. Suppose we have three different RSA users who all uses the value of e is equal to 3, but we have unique values of n, namely n1, n2 and n3. So if a user A sends the same encrypted message M to all three users, then the three ciphertexts will be M1, M2 and M3, and each will be taking a mod with a different n specified by n1, n2 and n3. However, it is likely that n1, n2 and n3 are pairwise relatively prime. Therefore, one can use the Chinese remainder theorem to compute the any number for m1, m2 and m3 using all three numbers n, and by the rules of RSA algorithm, m is less than each of the number n. Therefore, the attacker need only to compute the cube root of m, and this attack can be countered by adding unique pseudo-random bits strings as a padding to each instance of m to be encrypted. So as stated, we cannot similarly choose a small value of E, and we cannot also choose a small value for D for efficient operations. So decryption also uses the exponentiation to the power D, and a small value of D again is vulnerable to brute force attacks and other forms of cryptanalysis. So you can use the Chinese remainder theorem to speed up the computation. The quantities d mod p minus 1 n p minus 1 and d mod q minus 1 n can be pre-calculated, and end result is then calculation is approximately 4 times as fast as calculating m is equal to c raised to power d mod n directly. So before the application of public key crypto systems, each participant must generate a pair of keys, public key and private key. So you have to determine the two prime numbers. Prime numbers should be P and Q, and you have to select either E or D to calculate the other. So for the first, consider the selection of P and Q. The requirements were listed in the last few slides, that P and Q should be prime numbers and unique to each other. So because the value of n is calculated by multiplying of p and q, and it will be known to all the stakeholders and potential attackers. So prime must be chosen from a sufficient large set. If we have a small set, it is easy to guess the number n. So method for using or finding the large prime numbers must be reasonably efficient, so which is a quite difficult task, and at present there are no useful techniques that yield a large number of primes, so some other means of tackling the problems is required. So the procedure that is generally used to pick a random number, an odd number of the desired order of magnitude, and the test whether that number is prime, and if not, pick successive random numbers until one of the prime is found. So as an example, one of the more efficient algorithm for finding out the prime numbers is the Miller-Rabin algorithm, which was discussed in lecture number 5. With this algorithm and most of similar algorithms, the procedure for testing whether any given number is prime is to perform some calculation that involves n and a random number chosen integer a. So if the number fails the test, then the number is not prime. So if the number passes the test, the number may be prime or non-prime. So if the number passes many such tests, you can specify a threshold that if the number passes about 80% of the tests, then you may say that with the possibility of the 80% or the confidence of the 80% that the number is in fact prime. So the procedure for picking a prime number is illustrated in this slide. So first of all, pick an odd integer n at randomly. So this can be done using a pseudo random number generator. The next step is to pick an integer a which is less than n at random. So you perform the probabilistic test such as Miller-Rabin test with a as a parameter. So if n fails the test, reject the value of n and go to step number 1. So if n has passed a test, sufficient number of tests, then accept the n, otherwise go to step number 2. So it states that keep repeating the test until you have the confidence that your selected number is a prime number. To discuss the security of RSA, 5 possible approaches to attacking the RSA algorithms are discussed here. The number one is the brute force attack, and it involves trying all possible private keys. The second form of attack on the RSA is the mathematical attacks, and there are several approaches, all equivalent in effort to factoring the products of two primes. Similarly, timing attacks, these depend on the running time of the decryption and encryption algorithm. hardware fault-based attacks involve inducing hardware faults in the processor that is generating the digital signature. And Chaucer's ciphertext attack in RSA exploit the properties of RSA algorithm. So the defense against the brute force approach is the same for RSA as for any other crypto system, namely to use the large set of key spaces. Therefore, the larger number of bits in the decryption, it is better. However, because the calculation involved in both the key generation and encryption or decryptions are very complex, the larger of the size of the key is the slower of the system will run. Therefore, we can identify three approaches to attacking RSA mathematically. The first approach states that you have to factor n to its two prime factors. This enables the calculation of Gaussian functions p-1 into q-1, which in turn enables the determination of the decryption key by finding out the encryption key and taking the inverse with the mod Gaussian n. The second approach states that determine the Gaussian function directly without first determining the p and q. Again, this enables the determination of decryption function. And the thirdly, determine the d directly without determining the Gaussian function. So most of the discussion of the attacks of the RSA have been focused on the task of factoring the number n and into its two prime p and q. Determining the Gaussian function phi of n given the number n is equivalent to the factoring n. So these approaches are very similar. So with presently known algorithms, the determination of the decryption number d given the encryption number e and the number n appears to be least time consuming as the factoring problem. Therefore, we can use the factoring performance as a benchmark against which to evaluate the security of RSA. So if you use a large number n with the large prime factors, factoring is hard, but it is not as hard as it is used to be with the increasing power of the computation. But if you choose the large number n, you have the greater possibility that your factoring of RSA will take larger amount of time. So a striking fact about the progress is reflected in this table and concerns the method used in the RSA algorithm. And until in mid 1990s, factoring attacks were made using an approach known as quadratic sieve. The algorithm attack on RSA 130 is used on newer algorithms, and it takes about 20% of the computing effort required. So as you can see, the number of decimal digits have been increasing over the years, and the number of bits have also been increasing, and the date is specified that when the each of the cipher is decrypted using the attacks presented in the last slide. So a 232 bit decimal number bit RSA was decrypted in end of 2009. So the threat to larger key sizes is twofold: the continuing increase in the computing power and the continuing refinement of the factoring algorithm. So we have seen that the move in a different algorithm has resulted in tremendous speed up. We can expect further refinements in the algorithms, and the use of even better algorithms is also a possibility. So in fact, the related algorithm, the special number field sieve, SNFS can factor numbers with the specialized form considered faster than the generalized number field sieve. So this compares the performance of two algorithms. It is reasonable to expect the breakthrough that would be enable the journal factoring performance in about the same time as SNFS or even better. Therefore, we need to be very careful for choosing the key size of RSA algorithm. So if we needed yet another lesson about how difficult it is to assess the security of cryptographic algorithm, the appearance of the timing attack provides a stunning one. Paul Kocher, a cryptographic consultant, demonstrated that a snooper can determine a private key by keeping track of how long a computer takes to decipher the message, and it is applicable not just for the RSA algorithm but other public key cryptographic systems. And there are two alarming reasons that first of all it states that it comes from the completely unexpected direction, that you do not know the attacker or nor the timing to decrypt the message, and it is a cipher text only attack. The timing attack is somewhat analogous to a thief guessing the combination of your safe by observing how long you took to turn the dials from number to number. It is simple guessing that what have you typed in your text message by looking at the pattern of your fingers. The attack can be adapted to work with any implementation that does not run in the fixed time. So you can add the random variation of running time in the execution to resolve or dismantle such kind of attacks. Although the timing attack is a serious threat, there are simple countermeasures that can be used, including the following. So first of all, you can add a constant exponentiation time. So it will ensure that all the calculations take the same amount of time before running a result. So this is a simple fix but does not generate or degrade the performance. So if all the calculations take the same amount, you cannot guess which decryption is different from the other. Therefore all will look like same. Or you can add the random delay and it will better the performance. Better performance could be achieved by adding a random delay to the exponentiations algorithm to confuse the timing attacks. That means you can add some time to the attacks, to the calculations. And the author points out that if the defender do not add enough noise, attackers could still succeed by collecting the additional measurements to compensate for the random delays. And finally, you can add some blinding by multiply the ciphertext with a random number before performing the exponentiation, and this process just prevents the attacker from knowing what ciphertext bits are being processed inside the computer, and therefore prevents the bit by bit analysis essential to the timing attacks. Still, there is another unorthodox approach to attacking the RSA, and it is an fault-based attack. So, an attack on the processor that is generating the RSA digital signature. So, it induces the faults in the signature computation by reducing the power of the processor. The faults cause the software to produce invalid signatures, which can then be analyzed by the attacker to recover the private key. So the attack on the algorithm involves inducing a single bit errors and observing the result. So the author of these attacks show an analysis that can be done to demonstrate by extracting a 1 kilobit private RSA key in approximately 100 hours using a commercially available microprocessor. So this is a worthy of consideration attack. The attack does not appear to be a serious threat to RSA. It requires the attacker to have special access to the target machine, and it is able to directly control the input power to the processor, which is very difficult to get in most of the cases. So another form of attack is chosen ciphertext attack, and in the chosen ciphertext attacks, the basic RSA algorithm is vulnerable to this kind of attack. So the chosen ciphertext attack (CCA) is defined as attack in which the attacker chooses a number of ciphertexts and is then given the corresponding plain text decrypted with the target's private key. Therefore, the attacker could select the plain text, encrypt it with the target's public key, and then able to get the plain text back by having decrypted with the private key. The attacker exploits the properties of RSA and selects blocks of data that, when processed using the target's private key, yields the information needed for cryptanalysis. Clearly, this provides an attacker with no new information. Instead, the attacker can use the already guessing work. To counter such attack, RSA Security Incorporation recommends modifying of the plain text using a procedure known as optical asymmetric encryption padding. This figure shows an optical asymmetric encryption padding scheme. So as the first step, the message M to be encrypted is padded, and a set of optional parameters P is passed through a hash function h of P. The output is then padded with zeros to get the desired length in overall data block DB. Next, a random seed is generated and passed through another hash function called the mask generating function MFG. The resulting hash value is bit by bit XORed with the data block to produce the masked data block, and which forms an encoded message EM. Note that the encoded message includes the padded message, the masked by the seed, and the seed masked by the masked data block. The encoded message is then encrypted using the RSA algorithm. So that concludes today's lecture, and in this lecture we overviewed the working of RSA algorithm, the computational aspects of the RSA algorithm, that how much is difficult to encrypt and decrypt the RSA algorithm, and finally which discussed some concept about checking the security of RSA algorithm, and in which we discussed number of cipher attacks and to measures to overcome such attacks. So if you have any question, you can ask me, or you can read the chapter 9 of the recommended book for further studies. Thank you very much.